Okay, we've just determined that a pendulum of mass 0.5 kilograms and length 4 meters has an angular frequency of 1.53 radians per second, which entails a period of 4.0 seconds. That's not exactly 4 seconds, but to two significant figures, it is 4.0 seconds. Now, the mass didn't really matter. If you go back and look at how we calculated this, yeah, we did use the mass to define or to obtain the restoring force constant for the pendulum, which we could then use to calculate the angular frequency, which is used then to calculate the period. However, in our calculation, we noted that the mass term cancels out under the square root sign when we calculate omega, so that the mass didn't matter, and we would have gotten the same thing for any mass. We would have had a different force constant, but it would have been working on a different mass, and we would have ended up with the same angular frequency. Okay, now we want to model the motion of a pendulum with an amplitude of 12 centimeters. What can we determine about the motion of a pendulum with amplitude 12 centimeters? Well, the first specific question we're asked is, what's the total energy of this system? Now let's think about it. We have a pendulum. Here is its equilibrium position. Now it's going to move out to here, then back to here, and back to here, and back to here, and so forth. We have an ideal pendulum. We're assuming an ideal pendulum, so that the restoring force is a conservative force. So that when, let's just say the pendulum is initially at equilibrium, what does it take to get it into motion with an amplitude of 12 centimeters? Well, there are a couple of ways we can do this. One way is we can simply push on it until it's out here at 12 centimeters, then release it, and it'll go through its oscillation to negative 12, positive 12 centimeters, and so forth. When we do that, excuse me, the restoring force, which is conservative, ideally conservative in the ideal case, is pulling this way, and we're moving the pendulum this way. So the conservative restoring force is doing negative work on the pendulum, exerting a force this way when the pendulum goes this way, so that the net force on the pendulum and its displacement are in opposite directions. That conservative force, which is the net force, then does negative work, which, as we know from the definition of change in potential energy, increases the potential energy. Change in potential energy is equal and opposite to the work done by the conservative force. So that when the conservative force does negative work, as it does from here to here, the potential energy, change in potential energy, is the negative of that, making it positive. So we basically put energy into the system by moving it out to here and release it, and then the energy is maintained. There's no non-conservative force acting, so that there's no loss of total energy. What's the total energy of this system then? Well, total energy is just the potential energy when it's right here. Now, when it returns to its equilibrium position, the potential energy is back to its original amount. Okay, so and I should have said it earlier, but we're implicitly implicitly assuming that the potential energy is zero here, or more specifically, we declare that the potential energy is zero at the initial position. So the change in potential energy from here to here is the potential energy at this point. When the pendulum returns back to equilibrium, it will have lost that potential energy. Potential energy will be zero. Since there are no non-conservative forces, the total of kinetic and potential energies is constant. So that the lost potential energy appears as kinetic energy. So whatever the potential energy here is, that's going to be the kinetic energy here, and that allows us to calculate the velocity if we know the potential energy at this point. Okay, well, that's the idea. let's see how it works out. Okay, well, the total energy then is the potential energy at maximum distance. Maximum distance is, of course, the amplitude. That's at 12 centimeters. And maximum distance from equilibrium. Potential energy at position x, as we've seen earlier, is 1/2 kx squared. Remember that the restoring force at position x is 1/2 kx, has magnitude 1/2 kx. So that displacing from equilibrium to position x, the average force is going to be from 0 to kx, which is going to be 1/2 kx, and we're going to move through displacement x to get from 0 to position x, so that the work done is going to be 1/2 kx average force multiplied by x, the displacement. Now you can work that out more carefully with positive and negative signs and so forth, but that's what it comes out, and we've done that previously, so I don't want to go through all that right now. I just did, but I don't want to go into complete detail in interest of time. We assume that we know this at this point. So anyhow, the potential energy at maximum displacement, which is x equals a, is just 1/2 k times a squared. So if we know the amplitude and the restoring force constant, we can get the maximum potential energy. Of course, for a pendulum, k is mg over L, so that does depend on this m that didn't influence our calculation of omega. That was, again, dependent only on the length. Okay. Well, then, that is the total energy of the pendulum, since when the pendulum gets to its maximum displacement, it comes to rest for an instant before returning. So its velocity here is 0, its kinetic energy here is 0, all its energy is potential, and that's 1/2 ka squared. Okay, that is the total energy of the system. So we write that total energy is 1/2 ka squared. Okay, then, we also know that the total energy is the sum of the potential and kinetic energies, so that the kinetic energy is at its maximum when the potential energy is at its minimum. And the minimum possible potential energy is 0, which occurs at x equals 0. You fall back to here, your potential energy falls to 0. You start moving this way, and your conservative restoring force immediately starts exerting its force this way. So again, you're moving in one direction, conservative force in the opposite direction. The conservative force is doing negative work, the change of potential energy being equal and opposite to the work done by the conservative force is positive, so your potential energy begins to increase again. So again, minimum potential energy is 0, and that occurs when x equals 0, so that total energy is 0 plus maximum kinetic energy. In other words, you're going to get your maximum kinetic energy when your potential energy is at its minimum, which is 0. It follows that your maximum kinetic energy is 1/2 ka squared. Now our goal is to calculate the maximum velocity of this oscillator, of this pendulum. 4-meter pendulum, twice as long as I am tall, and then a little bit, pulled out 12 centimeters and released. It's going to oscillate fairly slowly because it's a pretty long pendulum, at least on the scale of what we're looking at here. So, how do we calculate this? Well, if we know the maximum kinetic energy, then we know m 1/2 mass times maximum velocity squared, because that's, of course, what the maximum kinetic energy is. If we know the mass, as we do, then we can solve this easily for V max once we know the maximum kinetic energy. Well, maximum kinetic energy is equal to the maximum potential energy is equal to the total energy. So we calculate 1/2 ka squared, which is the maximum potential energy, or the total energy, and we just plug in k, 1.23 newtons per meter, as we determined earlier, the 0.12 meter amplitude squared, and then the 1/2, and we get something pretty close to 0.009 joules, so our maximum kinetic energy is about 0.009 joules. Solve this equation for V max, and this is very standard. I'm not going to read it to you. We've done it dozens of times by now. Solving 1/2 mv squared equals kinetic energy for V, we get plus or minus the square root of twice the kinetic energy, in this case the max kinetic energy, divided by the mass. We plug that in, plugging in the 0.009 joules for our maximum kinetic energy are given 0.5 kilograms for the mass, and we get something on the order of something pretty close to plus or minus 0.19 meters per second. I think if you actually calculate this out, you'll come closer to 0.18 meters per second. I wasn't sure which way it went when I did the mental calculation, so I knew it was between 0.18 and 0.19. And there's no magic to that. Then we choose plus 0.19 meters per second because we're looking for maximum. But, you know, this isn't a vector quantity. We could have chosen either. But the maximum speed, and that's going to be the maximum velocity going through equilibrium from either direction, is going to be 0.19 meters per second. Now, there's an alternative way we could have gotten the maximum velocity using the unit circle, and we'll talk about that in a minute.